Let's look at another example of absolute extrema. Now, with the last problem, we noticed that we had no critical numbers. So that basically forced all the analysis to the boundary. I mean, the second partials test is very, very effective. However, we certainly have functions that are defined on closed bounded sets. So that's going to amplify the analysis. That is, we're going to have more work to do necessarily. So what I thought was interesting is that if we take that idea and we look at an example where we actually do have critical points and how that will impact the solution to the problem. So here we've got determine absolute extrema over the region R. Again, when we think about this, any extremum that we compute, for instance, it all has to do with the context of the problem. So just to make sure that you are classifying things correctly, think relative extrema, think absolute extrema, but it's certainly possible for a relative extremum to be an absolute extremum, depending on the particular circumstances. So we always have to make sure that we are considering the context of the problem. So for this particular example, we have determined absolute extrema over the region R, and we have a very symmetric function. F is x squared plus 2xy plus y squared, but that, of course, from algebra 1 is just a perfect square. And so that's going to have an impact on our analysis. And the region is a rectangle. That is, the absolute value of x is less than or equal to 6, and the absolute value of y is less than or equal to 5. So just with that, we get a nice rectangle here. Okay, so again, we'll have vertices 6, 5, 6, -5, -6, -5, and -6, 5, moving through all four quadrants. Now, before we look to the boundary, let's go ahead and consider the x and y partials. Again, when we take the x partial, we get a 2x plus a 2y. When we take the y partial, we get a 2x plus a 2y. Same equation, set equal to 0, the 2's absorbed. And in both instances, we get y equals the additive inverse of x. So right there, we have infinitely many critical points. And so this is the reason for the line y equal -x here, because that impacts our analysis and it runs right through the region. So we haven't had an instance where we've had infinitely many critical numbers or critical points. And so that's an interesting situation. But what we see is that it's a very simple one, because notice if we replace y with the additive inverse of x or the negative of x, then the function is identically 0. So again, by writing it with the perfect square, we can easily see that the function value is 0 for any points on this line here. So that simplifies our analysis. Now, one thing that we've noticed is that we're thinking, okay, so what kind of classification do we get for this infinitely many critical points? Well, let's go ahead and do it. If we do the second x partial, we just get a 2. And if we do the second y partial, we get a 2. And of course, the xy partial just simply is 2. So 2, 2, and 2. But we know that the d is the second partial of f times the second partial of f with respect to y, and then we have the square of the mixed partial. So we just get 0. Okay, so again, fxx times fyy minus fxy quantity squared. So we just get 0. Okay, there's no conclusion with that. The second partials test does not give us an answer because there is no firm answer. It could be many things. So when we have a test that's inconclusive, it doesn't mean that the test is bad. It's just that we don't get a firm result. Okay, so we write no conclusion, but we don't throw this out because it still can impact our analysis. So just like with the last problem, what we want to do is to analyze the value of the function on each of the segments, and it's very easy to do. So if we start with 1, we have y is equal to 5, and x runs from -6 to 6. So we can just simply replace the y with the 5 and write the region for the x. Now, again, I've just kind of notated the y is equal to equal to 5, so you can see that. Now, you think, okay, when will this be the smallest? Well, we simply know that we can make this 0 when x is equal to -5, so that was easy. And then how can we make this as large as possible? Well, how can we maximize x plus 5? Very simple, just like we did on the last problem. Replace x with 6, and of course we get 11 squared, which is 121. So we're going to see this 121 again, and we're going to see the 0 again. Okay, but notice this is what? This is -5, 5. Okay, when we look at that, that's this point right here, -5, 5. So that's not a surprise. We get that from this. So nothing new there. Now for 2, again, we have x equal to 6. So we replace x with 6 in the function, and then y runs from -5 to 5. And then if we try to minimize, we're thinking, how small can we make this? Well, when y is equal to -5, we just get a 1, and 1 squared is 1. But, then we think about that. Well, 1's bigger than 0. That's probably not going to have much of an impact, so we don't worry much about it. But then, of course, now we can certainly maximize this when y is equal to 5, and we get 121 again. So again, that's going to come up again, well, in every case. For 3, we have what? We've got y is equal to -5, and x runs from -6 to 6, again, like 1 in a similar fashion. And then we say, well, how can we minimize f? Well, of course, we can let x equal 5. Well, of course, now we've got 5 and -5, so we've got this point right here. Again, not a surprise. We knew that from this. And then again, we want to maximize, we can just let x be -6, and we get the square of -11, which is 121. Remember, the inner function of the square is just linear. So all you're doing is saying, okay, how can you maximize or minimize a linear function? Just like the last problem, that's very simple. But again, you have to exercise just a little bit of care to make sure that you're utilizing the given interval when you're doing that analysis. Now for number 4, notice here we have x is equal to -6, and then of course y is running from what? In this case, -5 to 5. So again, we just simply replace x with -6, and then we say, okay, how can we minimize this? How can we make this as small as possible? Let y equal 5, and we get the square of -1, which is 1. And then, of course, our friend, the maximum again, that we get, just like we always end up getting, we think about, again, how can we make this as large as possible? Well, we replace y with -5, and we get the square of -11, which is 121. Now, we see out of all of this that the maximum value is 121. And notice we see here we've got -6, -5, and here we have -6, -5. That accounts for this order triple. And then here we've got what? 6, 5, 6, 5. That accounts for this order triple. So the maximum of 121 occurs at 2 instances. Okay. Now, when we think about the minimum, well, the one, like I said before, we don't care about that. We've been able to lower that to 0. So we get the minimum of 0 right here. That is on this blue line here when y is equal to -x. And so again, we have infinitely many instances of that. That is x, y is -x, and the value is 0. So what we see with this problem is just a very interesting connection between the ideas that we utilized in Calculus 1 that have been transferred to Calculus 3. However, now we have more complicated regions. Before we had closed bounded sets, now we have closed bounded regions in the plane. So that's going to amplify the analysis. But if you think about it, and this is what you should do, for each segment, that's just a microcosm of calculus 1. As we go to a vertical segment, that's a microcosm of calculus 1. So we're doing calculus 1 on each of the 4 segments of the rectangle, just like we did calculus 1 on each of the 3 segments of the triangle. This, however, is just a little bit more interesting, the way it's set up. So just remember, just like in calculus 1, we want to check for the interior critical points, and then we want to consider the boundary, just like we have done in our previous courses. And we are done.